Okay, so this is Taylor and Laurent series for Math 423. This is the statement of Taylor's series. So we have a disk of radius r centered at z0, and our function is analytic everywhere inside that disk. And then for all z inside this disk, we have Taylor's theorem, right? And if we use the notation that f to the parentheses 0 is z, that's this part, then we have, we can write it as a sum. Laurent series is similar. F of z is analytic at all points inside and on an annulus. And remember that this kind of a figure is we have a center that's Z0, an inner ring that's by R1, and an outer ring that's R2. And we're analytic everywhere in there and also on the boundaries, which is a little bit different from the statement of Taylor's theorem. So it means we're actually analytic on an open set that contains the annulus. So for all z inside this annulus, we have this theorem, which is similar but not quite the same. Our coefficients aren't phrased in terms of the derivatives, but it's a series. We're allowing negative powers here. And then we have the coefficients are given by these theorems. So the method of proof for Taylor series, which we're going to do first, is we have the Cauchy integral formula for f of z, and we will expand that in a series basically and then integrate it term by term. So what we want to do first is say what we're going to do, which is proving Taylor's theorem. We need a lemma first, which is that for all z not equal to 1, for all n greater than or equal to 1, so n here is a positive integer, we have 1 over 1 minus z is equal to 1 plus z squared plus dot 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 plus z to the n minus 1 plus z to the n over 1 minus z. And you can prove that just by multiplying both sides by 1 minus z and getting it to work. Remember that you can't have z equal to 1 because it gives us 0 in the denominator. And this works for any n that you want. So what's my elevator proof? Um, Cauchy integral formula. So what's our elevator proof for that? Use the Cauchy integral formula to get, because we want f of z equal to something. Um, and then we'll expand this using the lemma that we have above, integrate each term, and that'll give us a remainder. We'll be able to integrate each of these terms, the 1 plus z squared, blah, blah, blah. And then the remainder there, we'll show that goes to 0. So idea is pretty straightforward. It's actually a pretty straightforward proof. It just is, got a lot of bookkeeping in it. So f of z, we don't want to do that yet. We want to draw a picture first. So our picture is that we have a center z0 and a radius r, and we're analytic inside that disk, but not necessarily on the boundaries. So that means when we're doing our integral, Our integral actually can't be on the boundary because we don't know it's analytic there, but we have to take some point inside there. So we'll let z be inside of this disk. Then z is some point. We'll call that z, and we'll call the distance that z is from z0, we'll call that r. That's supposed to be r. So to be able to use the Cauchy integral formula, we need to have a path that goes around z and around z0. So since z is inside, that means that r is strictly less than r. Let rho be such that 0 is less than r is less than rho is less than r. So we'll take another distance, we'll call that rho, and then we can draw a circle of radius rho. And the point about this circle, which we'll call gamma of t, equals to z0 plus rho e to the it, 0 less than equal to t, less than equal to 2 pi, and we're going around it like that, so that z0 is on the left. F of z is analytic inside and on that path gamma of t. So that means we can use the Cauchy integral formula using that path of gamma of t. So f of z, and we'll do a semicolon, and we'll just let alpha be points on that curve. So f of z is, using the Cauchy integral formula, integral 1 over 2 pi I, integral around gamma, f of alpha over alpha minus z d alpha. Right? So we're integrating around the curve, gamma. So our variables on that curve, alphas. So what do we want to do with this? We want to use this lemma somehow. So we need to do a little bit of rearranging. We will rewrite this as 1 over 2 pi I integral around gamma f of alpha over alpha minus z0 plus z0 minus z. So that's a thing we can do, d alpha, and we'll regroup that a little bit. Gamma alpha minus z0 minus z0 minus z, f of alpha on top, and a d alpha. Okay, so that's set up nicely. Point is that alpha minus z naught is bigger than that. So the distance between any point on this circle to z naught is rho. The distance from z0 to z is r. R over rho is less than 1, and that's going to actually get us that our remainder is going to be 0. But we need to get some work done to get there. So what does that tell me now? F of z is 1 over 2 pi I, integral around gamma. I'm going to factor out a 1 over alpha minus z0. That'll leave me with an f of 0 over 1 minus plus z. Oh, I got my signs wrong. This should be minus z0 plus z there, right? If I factored out that minus sign, right? Which is supposed to be z minus z0 over alpha minus z0. And the point is along the way, oh, this should be an alpha, along the way is that this fraction here in the denominator, its modulus is less than 1. Okay, so what does that give me? Well, now I'm going to use my lemma because this is 1 over 1 minus, I'll rewrite it in a slightly different way so it's clear what my lemma is. Gamma f of alpha over alpha minus z0, 1 over 1 minus the quantity z minus z0 over alpha minus z0 d alpha. So here's the thing that I'm applying my lemma to, right? And this is my lemma, and this works for any n, right? So we'll pick an n. What do we have? We have f of alpha over alpha minus z0, and then we get this expansion. And this expansion is where the annoying bookkeeping comes in. So this becomes 1 plus z minus z0 over alpha minus z0 plus z minus z0 over alpha minus z0 quantity squared plus dot 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 plus z minus z0 over alpha minus z0 quantity to the n minus 1 plus the really nasty fraction, which is z minus z0 over alpha minus z0 to the n over 1 minus z minus z0 over alpha minus z0 and parentheses d alpha. Okay, so um, not horrible. So what we can do now is we can distribute the alpha minus z0. We're going to distribute this one. And well, we'll distribute this whole thing and turn it into a bunch of separate integrals. Remember, we only have a finite number of integrals here. There's n, so we can just integrate them one at a time. So we get f of 0 is 1 over 2 pi I integral around gamma f of alpha over alpha minus z0 d alpha plus 1 over 2 pi I integral around gamma uh, z minus z0 times f of alpha over alpha minus z0 squared plus 1 over 2 pi I integral around gamma f of alpha z minus z0 squared times f of alpha. Oh, there's a d alpha here. Over alpha minus z0 cubed. Remember, we're distributing this alpha minus z0, so we get 1 here, 2 alpha minus z0s there, 3 there, plus dot dot dot, plus 1 over 2 pi I, integral around gamma, z minus z naught to the n minus 1, f of alpha, over alpha minus z0 to the n, the alpha, plus the annoying term, and that's that last one. So 1 over 2 pi I, integral around gamma, f of alpha, z minus c naught to the n. Well, we'll just leave it as z minus c naught over alpha minus c naught to the n over. Now we're going to bring in this alpha minus c naught and multiply it by all this stuff. 1 minus z minus c naught over alpha minus c naught e alpha. Great. So what actually is this? Well, we can recognize a lot of this is just being derivatives, right? So f of z, this first term, that's just Cauchy's integral formula for the function. So that's f of z0. The second term, remember that the z minus z0 is constant, right? Because we're integrating with respect to alpha. So this term has got an alpha in it. This term has got an alpha in it. This term doesn't. So we can factor that z minus z0 out of the function. And then we have 1 over 2 pi I times the integral of f of alpha over alpha minus z0 squared d alpha. And that we recognize as f prime of z naught because of Cauchy's integral formula for derivatives. Likewise, this one, the z minus z0 squared comes out of the integral. And what we're left with is 1 over 2 pi I f of alpha over alpha minus z0 cubed d alpha. And we can recognize that as almost being Cauchy's integral formula for derivatives, but it's actually 1 over 2 factorial times the second derivative at z naught. Plus dot 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 plus, so z minus z naught to the n minus 1. Right, that factors out of that, and then we're left with an alpha, f of alpha over alpha minus z naught to the n. So that's the nth derivative, but we need to have that n factorial floating out in front. And then we have the annoying remainder term, which is, oops, so that, let me undo this a tad. So that's going to be, again, I can factor out the z minus z naught to the n. Right? Oh, fudge. That's the n minus 1 derivative at z naught. And this is over n minus 1 factorial. So z minus z naught to the n, that'll factor out. I'm left with a integral around gamma, f of alpha over alpha minus z naught to the n, and that takes care of this numerator, and then that's times 1 over, well, I'm going to distribute this thing in, alpha minus z naught. So we'll distribute that to the 1, and then we distribute this to this term, but the denominators cancel out. We get a minus z plus z naught d alpha. Oops. We want to apply our ML theorem to this. And notice that the z zeros cancel out here, so we just have an alpha minus alpha. And just to remind people of what the various things that are going on here, we have a disk, we've got a z0, we have a radius capital R, we have some point z that's a radius little r, and then we have the circle that we're integrating around that's at a radius rho. So what do we know here? Well, we know that z minus z0 is equal to r, but that's sort of that definition. We know alpha minus z0. Alpha is some point on this circle, and that's a circle of radius rho. What we also know about alpha minus z is here and alpha is this. So the closest they can come together is rho minus r. So that has to be greater than or equal to rho minus r. So we will let k, for example, be the maximum of the modulus of f of alpha on gamma of t. So it's the biggest that f is on that thing. then the modulus of f of alpha over alpha minus z0 to the n, alpha minus z is less than or equal to, well, this part is in the top, and we know that's less than k. This part in the bottom, we know that's actually equal to rho, so we don't need to do any estimates there. Alpha minus z, we know that's got to be bigger than rho minus r. That means 1 over modulus alpha minus z has to be less than or equal to rho minus r. And so we can put that in there because it's a less than, we're looking for less than. So it gives us a bound on our integrand. So, oh, we wanted a thing on here. And the other thing we need is the length of the path, but that's just 2 pi rho. So what we have then integral around gamma f of alpha over alpha minus z naught to the n alpha minus z d alpha is less than or equal to, well, we have 1 over 2 pi. Z minus z naught we know is r, so that's an r to the n. And then this whole thing in here is this thing. That's the maximum of the integrand, of the modulus of the integrand. And then a 2 pi rho out front, because that's the length. So our remainder term in modulus I should have just done dittos for this so I didn't have to write it out again. 2 pi's cancel out. We have a k, which is our maximum of the function, times the rho over rho minus r. And then we have r over rho quantity to the n. There we go. So if we define the nth Taylor polynomial, as we usually do, f, well, we got to the n minus first derivative, I think. Then what have we actually shown? We've shown that f of z minus Tn of z, right? That's the polynomial. F of z minus this polynomial is equal to this integral, but that integral in absolute value is less than or equal to k rho over rho minus r, r over rho to the n. And as n goes to infinity, so the limit of n goes to infinity of that is that, and so f of z must be equal to t infinity of z, which is the sum from k equals 0 to infinity of f k at z naught over k factorial e minus z naught to k. So there is Taylor's theorem. So pretty standard. We got a remainder. We showed it went to 0, so that these things have to be equal to 0, have to be equal to each other. Idea is pretty straightforward. It's the Cauchy integral formula. We just needed to use this lemma and the fact that we can set up this circle that's outside of Z to do the integration around so that we can get everything to go to zero. One of the things that sort of is left unstated or unproven is whether or not this just tells us that analytic all points inside of a disk, Z0, comma R, and we have that for all this kind of uh, formulas. And then this question is how big can R be? And does it have to be a disk or could it be something else? Which are things that we'd have to look at going forward. Laurent series theorem is the same kind of thing with the same kind of argument. You have to be a little bit careful here because if we think about the annulus, right? We'll draw a picture for that. I'm not actually going to do the proof, but the idea is that you have Z0 inside an annulus like this. What we don't know is whether or not the function is analytic inside of here, right? Inside of the smaller disk. We just know it's analytic out here. So if we do Cauchy's integral formula, we'd have to do it around a little piece, a little circle for my z that's in here, because we want our function to be analytic inside of that, and then we can use Cauchy's integral formula. But this circle, we can actually replace that. Instead of doing the circle, we can say start here, we'll go up to here, go around this, come back, go back in, go around there, come here, go around this way because we need to have the analytic area on the left, come back up, and then finish out. Or whichever way we're going around. I guess we're going around that way. Then we go around here, and then we come back. So we can replace this by an integral around the outer side minus an integral around the inner side. And that's why we get these two different things, because we have to, this part comes from the integral around the outer ring, and then this part comes from the integral around the inner ring. The point is that if we do the same kind of thing, R2 is bigger than Z, and then Z modulus of the distance from Z to Z0 is bigger than R1. And so when we do this kind of, when we use this, why my brain is fried. When we use this lemma for the inner ring, we have to do a reciprocal there so that we have the proper thing. We end up with a R minus an R1 minus a Z minus R1. And then we have to use that as the integrand. So for the Laurent series, it's pretty much the same kind of setup going through all this stuff. You just have to be careful about the inner one because you have to be a little bit more careful about the application. Notice also when we're looking at the Laurent series, as we go back up here, we can't actually turn this into a derivative, right? That's not Cauchy's integral formula because we don't know that the function is analytic everywhere inside of that, right? It might not be in the analytic inside of here. So that's Taylor series and Laurent series. We'll pick up with that on Tuesday.